So when we do ANOVA, before we talk about the details of how it works, and ultimately in introductory statistics, I want you to understand the hypothesis of ANOVA, a little bit conceptually about how it works, and then we're going to use technology. We're going to use a TI-84 to run them in this class, and you make the interpretation. So you don't have to worry too much about the particular computations and details in this introductory class, but you might if you're taking a more advanced class. But the conditions that we have, so we're comparing the mean from a bunch of different groups. Let's say that that's I, capital I, just to have some variable to call it. We need simple random samples from all of those. Okay? All of the probability procedures, inferential statistics, the ideas, the p-values, they're based on simple random samples from each group, each population. Also, we're making the assumption that the ith population, so every one of them, has a normal distribution with some unknown mean that we could call mu sub I. And of course we know that we get the central limit theorem for sample means when we get larger and larger samples. And one way ANOVA tests the null hypothesis that all of the population means are the same as each other. And then there's also another assumption that is used in the computations. The computations involve using what's called a pooled standard deviation, where you're combining the standard deviations to come up with a measure of the standard deviations for the whole entire thing. And so we're using an assumption mathematically that all of these populations have the same standard deviation, sigma. And that might seem like a pretty big assumption, but in practice they just have to be close enough together. And so as it says here, the results of the ANOVA F test are approximately correct when the largest sample standard deviation is no more than twice as large as the smallest. Okay? So if you take your smallest and you double it and none of the others are bigger than that, then they're close enough together to reasonably run the ANOVA test. And so here's the computations. Okay, so I don't want you to memorize these formulas. I don't require in the introductory statistics class for you to actually compute these by hand. We're going to use the calculator, but I would like you to have some idea of what's going on. Okay, so the F statistic, it's actually a fraction. It's the variation in the sample means, how far apart the means are, divided by a measure of how spread out the groups are, variation among individuals within the same sample. Remember that I said, we showed some pictures, and I said if you have the data that's really spread out, then you're going to expect to find some differences in the sample means just based on how spread out the data are in doing random sampling. And then the less spread out they are, you expect those differences to be a little bit smaller. So they divide by that. You have the variation among the sample means, how spread out the means are from each other, divided by some measure of how spread out the individual groups are, and then kind of a combined measure of that. And so we have these things they call the mean squares. You're doing a bunch of squares in the formula. So the measures of variation in the numerator and denominator are called mean squares. You have the mean square for the groups, or sometimes this is called the factors, because it's, if you think of doing an experiment, your groups have different treatments or different factors. On our TI-84 calculator, the information for the numerator, it uses the term factor. And then the denominator uses the term error. So you have the mean square groups. That's a measure of how, basically it's a measure of how spread out the means are from each other. If you look at the formula there, each of the terms there, the sums on top, they involve taking your group mean minus the grand mean. The x bar here is the mean of the entire sample if you added all the groups together. So you're measuring how far each group mean is from the overall mean, squaring them so that you don't cancel out differences. And then it's a weighted average because you have different sample sizes. And you divide by the number of groups minus 1. So it's basically an average of how spread out the means are from what we could call the grand mean, the overall mean of the entire sample population across all the groups. And then the one on the denominator is a measure of standard deviation. It's sometimes called the pooled standard deviation, or if you the term there is actually the variance, the squared term. Take the square root of that and you'd get the pooled standard deviation. So the mean squared error itself, if you look at it, is basically a weighted average of the standard deviations. I call it a weighted average because you have different sample sizes. So you have to multiply by the different degrees of freedom there, the n-1s for the different groups in your samples. So those are the computations. You get this measure of how spread out the means are. You get this measure of the standard deviations, and you divide them. And that's the test statistic, which has a distribution, and we can compute probabilities with software or tables. There are 2 degrees of freedom. We've talked about degrees of freedom on our other hypothesis tests where we have distributions. like the one sample t-test, the degrees of freedom were n minus 1. We had this big formula that the software can compute for the two sample t-tests. For ANOVA, there's 2 degrees of freedom, one for the numerator, one for the denominator. And the computations, let me go ahead, I have some animations here to summarize it. The degrees of freedom for the numerator, which is always a smaller number, it's just the number of groups minus 1. Okay, so if I have 5 groups, that would be 4. If I have 10 groups, it would be 9. And then the bottom one, the degrees of freedom for the denominator, winds up being your total sample size, capital N. If you were to add up, each group has its own little n, N1, N2, the number in each group. If you add all those up, you have what I would call the total sample size, okay, across all the groups. You do that minus the number of groups, and that's your second degrees of freedom. So if you're trying to match up, if you were going to use a table, you would have to go and try to match up to the particular distribution, and it requires 2 degrees of freedom. The first one is the number of groups minus 1. The second one is the total sample size minus the number of groups. And we typically report these things. Like if we want to say the test statistic, we would say F parentheses, say 4, 15 or something, whatever the degrees of freedom are. We write them like that with parentheses. And here's just another summary, an overall summary of ANOVA. Okay? So ANOVA, you have I different populations, and you take your samples from those, and you want to compare the means across all of those. And the overall test tests the null hypothesis that there's no difference at all across all of those means. If there's I of them, that mu1 is equal to mu2 is equal to mu3, all the way out to mu sub I. And then the alternative, we really have to say this in words. A common mistake is to write the null hypothesis with not equal to's. If you do that, you're saying they're all completely different from each other. The alternative is just that there's at least one that's not the same as all the others. There's some sort of difference in them. And our test statistic is this big fraction, F, which is your mean square groups over your mean squares error. And we have those big formulas. The one on top is sort of a weighted average of how far the group means are from the grand mean. And the one on the bottom is a weighted average of the standard deviations. And when h sub 0 is true, you have an F distribution with I minus 1, number of groups minus 1, and capital N minus I, total sample size minus the number of groups for your degrees of freedom.